All right, welcome back, everyone. I'm joined by Priya Wadhwa, who's going to take you on a lightning tour of the Chainguard factory. All right, Priya, take it away.
Thanks, Mandy. Hi, everyone. My name is Priya. I am an engineering manager here at Chainguard, and I've worked here for over 3 years. So I've really seen this factory grow from what was probably just like a few simple build scripts to the actual like full-fledged factory that it is today. So I'm really excited to talk about this. Let's just dive right in. So before we kind of get into the factory itself, the inputs, the outputs, and all the stuff that happens inside, I want to touch on our SLA, which drives a lot of the decisions and the requirements of the factory itself. So our SLA is around CVE remediation and states that Chainguard will make commercially reasonable efforts to patch critical CVEs within 7 calendar days and high, medium, and low severity CVEs within 14 calendar days. So as we start to cover the factory, we'll want to keep this ultimate goal in mind. So my goal is that by the end of this lightning talk, you'll understand this entire diagram. It's a little confusing right now. And it's a pretty simplified model, but I tried to just include the highlights of our factory that we would cover today. I don't really expect this to make sense right now, but we can just start at the beginning. So on the very left-hand side, you can see that the input to our factory is source code, and that feeds into Chainguard OS, which is our own Linux distro. So we'll just dive in and start there. So this entire talk could probably just be about how hard it is to bootstrap a new Linux distro and keep it maintained, but I'll just cover the super high level ideas behind it. So we designed Chainguard OS to be a minimal hardened Linux-based operating system. And every single package is built from source. So that's kind of why source code is the input to our factory. The cool thing about it is that it's designed for continuous nano updates. And this basically means that any time an upstream open source project that we support releases a new version, we attempt to pull that latest version into the distro as quickly as possible. We'll grab that new version, update the package, run tests on it, and it should be merged pretty quickly within a couple of days in like the longest time frame. And that allows us to keep our images up to date and always have like the latest version of an upstream project available to our customers. This is the foundation for the suite of Chainguard products, and we have thousands of source repos, which turn into thousands of packages, which ultimately underpin our catalog of 1,600 plus images. We have a pretty impressive build system behind this, which is responsible for kind of building all of these packages, figuring out the dependencies between the packages, building the DAG of all the different packages, and then rebuilding packages every single day. We have a separate build system, which is then responsible for building the images on top of those packages. So there's a lot going on in this factory. Okay, cool. So let's take a quick look at the packages themselves and how they're defined. So as I said before, we build our packages from source. This is a pretty simple package spec that I chose. There's thousands of these. I picked this one because it's short and it fit on the screen. It's just a basic Go binary, Go vuln check. I think it's responsible for finding vulnerabilities in Go programs. But firstly, we build all of our packages from source. So you can see in this pipeline section, which is the build pipeline for building this package, we check out the source code at the expected tag and the expected commit to make sure we're getting what we expect to get. We also have a test stanza in the package. So at the package level, we run pretty basic tests, but we want to make sure that the binary that we're compiling actually executes. We'll run some basic tests to make sure functionality works. In this case, it's a pretty simple Go binary, so we don't have to do too much at this level. And finally, this little update stanza, I think, highlights some of the automation and the bots that we've built. So this is kind of where we're starting to get into the automated pieces of the factory. Since we have thousands of packages and we want to continuously update them to the latest and greatest version upstream, we have bots that watch our releases upstream. As soon as a maintainer upstream releases a new version, we want the package to be updated as quickly as possible. So this update stanza kind of gives a little signal to our automation to tell them how to watch for new releases. In this case, we're probably looking for Git releases. And when a new release comes up, we want to strip that V prefix off of it to determine the version for that next version of the package. So here's what it kind of looks like in practice. I just grabbed this random package update, which happened in Wolfie last week. I guess Contour released a new version, 1.32.1, and it was actually pretty cool. I went back in time to see what time the upstream project had released. So Contour released this new version at like 10 in the morning Pacific time, because I'm based in San Francisco. And at right around noon, one of our bots opened up an update to our package. So within 2 hours of the release going out, we had the update PR. On the right side, you can see it's a pretty simple change. We just need to update to the latest version, change the epoch, and then update the expected commit of the source code. Once this PR is opened, we run a bunch of checks on it. So we'll rebuild the package, we'll retest the package, we'll scan for vulnerabilities, scan for malware, and a few more checks as well. If everything is green, and only if everything is green, we also have bots auto-merge this PR into the distro. So this is basically how we manage to keep the majority of our packages up to date. We rely heavily on automation. Say something goes wrong here, and like one of those pre-submit checks fails, one of the tests fails, or something is just incompatible. That's when one of our engineers steps in, takes a look, and then they manually merge the package whenever it's ready. So it's pretty cool to see, actually. I think looking at the timeline for this specific package, it was merged within 4 hours of the release coming out upstream. It might give you a little hesitation. Like, is it really safe to merge things so quickly? That's kind of where the testing comes into play, and all the various scans that we do to make sure that there are no regressions as we upgrade. Great. Okay, so we have the first little bit of our diagram in here now. Source code feeds into Chainguard OS. We build packages from that source code. We test those packages, and then we have bots which keep those packages up to date. So then that brings me to Chainguard container images, which is our images product. So these images are composed of the packages that we just talked about. And there's some like interesting principles with our images. The first one is that they're minimal. Only the packages that absolutely need to be in there for the image to function as a drop-in replacement exist in that image. So we try to keep the surface of the image and the size of the image as small as possible. These images are also built, tested, tagged, and signed every single day. So on the right side, you can see our Python image was last changed within the last day. So would have been rebuilt every single day. We also build every single supported version that the upstream version supports. So even though we have a catalog of 1,600 plus images, our build system actually needs to be able to handle building multiple versions and variants of those images. So we're actually building 5, 10x the number in the catalog every single day. In this case, we support Python from versions 3.10 through 3.13. And all of those would have been built every single day, tested, tagged, and signed. Each image also comes with an SBOM, so you can see the provenance of an image. This basically tells you exactly what packages went into creating the image that you're trying to run. So in this case, we're still looking at Python. You can see a bunch of packages in there required for Python to function as you would expect, the version of those packages, and the license associated with each package. So we have a little bit more of our diagram. The packages feed into Chainguard container images. Those packages are compiled in a minimal way to build an image that is as small and hardened as possible. And images are built every single day before they're synced to your registry. So you might be wondering about CVEs at this point, because that is kind of a major selling point of the product, and also the SLA that I had mentioned earlier. How do we keep our images CVE free? So one of the principles I mentioned earlier is that our images are minimal, and this actually gets us a long way towards keeping images CVE free. Just reducing the number of packages that are in the image and only including what's needed means that the general surface for vulnerabilities is lower as compared to the upstream image. Additionally, the fact that Chainguard OS does those continuous nanobumps I was talking about earlier also helps us stay just generally lower in CVEs kind of for free, because we're always pulling in packages at the latest version. So as soon as an upstream maintainer kind of cuts a new release that remediates a CVE, we've pulled in that CVE remediation usually within a day or two. And this is a little different from other distributions, which might be on more scheduled release cycles and can't pull in those patches as quickly as we can. So I think some of the minimal aspect of Chainguard images and the fact that we're on this rolling distro contributes heavily to us being able to keep our CVE count low. And you can see Python, this image is free of CVEs as of 1 day ago. We scan images every single day, and that's how we can be confident that they're free of CVEs. But of course, sometimes CVEs do pop up. So let's cover what we do when that happens. So occasionally we can actually patch some of these CVEs ourselves. We have bots that will attempt to remediate CVEs in upstream code whenever possible. Sometimes it's just a matter of upgrading the dependencies in the upstream code. It can actually lead to kind of an interesting situation where we've patched a CVE before the upstream project has gotten to patching that CVE. And so we might be running like a slightly different version of the code than upstream is because of those patches. But as soon as upstream manages to release a new version that patches the CVE, we ditch our patch and we go right back to the latest version. Try to stay as close to the upstream source code as possible. And the final piece of this is our security advisories. So we file an advisory for every CVE that we find in a package. It can be a little confusing. We scan all of our images. We get the CVEs in those images, but those CVEs are tied to our packages. So we actually file advisories at the package level. If a CVE is found in an image, then we'll file the advisory for it. Some advisories can be added in with automation with bots that we're running. Typically, this is when a CVE has been fixed by upgrading to a new version. So the bot will just add in a little advisory saying, oh, the CVE for this package was fixed by bumping to this latest version. Sometimes we actually need an engineer to go in and to triage the CVE and determine if it's a true positive or a false positive. Something interesting happens if it is a false positive. So you can see on the right side an example of one of our advisories. This is for our gitness package. So the CVE ID is in there, some aliases, the timestamp for when the CVE was discovered. This one's kind of old, back from 2023. But at that time, one of our engineers would have gone in and investigated the CVE. They would have read up on the CVE details. They would have looked at the upstream source code and tried to determine if the application was actually susceptible to the CVE. In this case, our engineer decided that the CVE was actually a false positive that was coming up in the scanners because the CVE only affects Windows and our images don't run on Windows. So the cool thing about this is that when our engineers determine something as a false positive, they file these advisories, and those advisories are actually fed back into the scanners. So the next time that someone scans the gitness image, the CVE actually won't come up because it is a false positive. So you can be a little bit more confident in your scan results as well. You should only see true positives come up in the scan. So this is kind of another view of back to our Python image and the CVEs that we've discovered over the past couple of months in this image and the status of those CVEs as determined by the advisories on the package. So at the bottom, we had a CVE that was found on June 20th and fixed about a week later. There's a few more CVEs that have been discovered since then. Some of them are pending upstream fix, which means that we basically need to wait for the upstream maintainers to patch that CVE. One of them was fixed, one was under investigation and remarked as also pending upstream fix. So that kind of brings us to the end of this simple Chainguard factory diagram. Source code feeds into our Chainguard OS. We have bots which keep those packages up to date. We have bots which remediate CVEs, bots which file dependencies, bots which scan our images every single day. It depends heavily on automation. Behind all this are some really impressive build systems which build thousands of packages, thousands of images every single day. And what really kind of holds us all together is our testing strategy. So we have testing at the package level and thorough testing at the image level, which functionally tests our images before they're synced to your registry. Okay, cool. That's all I have. I hope that wasn't too fast. If anyone has any questions, be happy to try to answer them.
Hey, thanks, Priya. I love hearing all about our automation that runs our factory. So we learned that this platform is really strict on time. It will kick us off. So we don't have time for a lot of questions. And when we 50 after the hour, it's going to kick us off and you can join the next session by joining in the agenda tab. But folks do have some questions in chat for you. First off, we must be monitoring a lot of upstream repos. Do we have any idea how many we monitor?
That's a good question. I mean, I think the stat I had was like we have like 8,000 plus source repos, so I would imagine most of those are being monitored.
Yeah, that makes sense. That sounds about right. Okay, let's stick in one more question. Folks want to know what tools and tests we use to ensure that no malicious code is injected in the upstream repositories.
It's a good question. I know we run some malware scanners. I don't like, I would have to dive into it to check out the specifics. Probably someone on our security team would be better to
I totally
answer
understand.
that. I'm sorry.
All right, well, how about one more I know you know the answers to. Where did our SLA numbers come from? Where did we come up with the 7 and 14-day numbers?
I think that came from FedRAMP. So I think FedRAMP states that you have 30 days to look at critical CVEs, 90 for maybe low, medium, or sorry, high critical have 30 days, medium has 90 days, and then low has 180 days. So our 7 and 14 is much shorter timeline than that.
Yeah, Dustin says FedRAMP indeed. That's exactly where those numbers came from, and we remediate much quicker than that. So, so that we don't cut you off, let's go ahead and thank you, Priya, for your awesome talk. And let's go ahead and jump to the next session where we'll welcome Cy Venom from AWS to show how EKS, Automode, and Chainguard work together. So join the talk by clicking the link in your agenda tab. Thanks again, Priya, for being here today.
Thanks, Andy.